Hi folks, welcome back to Physics with Captain Rod. I'm making this video here to provide an example for you of how to use kind of graphical techniques to analyze the motion of an object moving under the acceleration of gravity. So what we're going to do here, we're going to take a look at this one. Standing on the top of this 10-meter tall building, young Timmy here throws his ball up at 5 meters per second. How long does it take before it hits the ground? So what I mean by that is Timmy's going to throw the ball in this direction at 5 meters per second. So initial velocity 5 meters per second, and it does something like this. Boom. Here's a picture right here, right before impact here. Now we're going to calculate a couple things. One, how long, and I meant time-wise, before it hits the ground, and then second question here, how high does it get? Like, what is the maximum point like in this problem? I should put that ball right about here in my picture. Now, typically with these motion problems, you start here thinking about the acceleration. Now, the ball, even though it was thrown upward, the acceleration direction is down. That'll become a little more clear when I draw that velocity graph. In fact, why don't I start with that? All right, at t equals 0, the velocity is plus 5 meters per second. Oh, I should back up. I haven't defined a set of coordinates yet. How about we put an origin here, x, y, and we will use the y coordinate here to keep track of the location of that ball. So now that we've defined up as positive, that initial velocity at 5 meters per second is some positive number. So we go to our velocity graph at t equals 0, our velocity 5 meters per second. Plus 5 because it's in the direction we call positive. Now remember that this ball is going to slow down. Gravitational acceleration is approximately 9.8 meters per second downward. I like to round that and say that's real roughly approximately 10. What that means is this ball is moving at 5 meters per second up, but a second later its velocity is going to drop by 10 meters per second. So it's going to be, it's going to put us like here on the curve. This graph is looking like this. And what we're going to do here is actually take this a little further and just put t here, because we want our equations to be good for all time. Now you'll notice this has negative acceleration the other way, or the entire time. So the acceleration of that ball again is 9.8 meters per second down. So when we represent that graphically, going to look like this out to any time t here. And when we do our y coordinate here, the y coordinate starts out at 0. Now initially, as time goes on, the ball hits some maximum value, and then the y coordinate is 0 again, and then it's some negative value. So this graph is looking something like this. Now, the million-dollar question is, how do we go through and write equations for these graphs? So, all right, from here to here, your acceleration is delta v over delta t. It's pretty easy to rewrite that. Delta v equals acceleration times delta t. In this problem, our delta v, our change in velocity, is v final, which I typically just call v, minus v initial. And our acceleration is 9.8 meters. Oops, I'm going to leave the units off. Put NCU for note consistent units. So that's going to be 9.8 t, and the acceleration is down, so it's negative. Always have to be consistent with your coordinate system. Gravitational acceleration points down, we've got up positive. That's why this minus sign right there. So the equation for this line is v equals 5 minus 9.8 t, or you can write it negative 9.8 t plus 5 if you wish. All right, next. Going from here to here. Now, here's some things about these, and I imagine this can be pretty confusing. if you want your equations to be good for all time, you have to pick kind of a generic time. So what I like to do is just take this first little time interval. I'm just going to stop here and just give this a temporary name, t. And write this out. Velocity is change in y over change in t. So our change in y is velocity times change in time. Now, this velocity, remember, is an average. And what I'm going to do is use this area right here to represent the change in t, or the change in y, out to any time t. And this point, what you have to imagine is as we move along this curve here, the equations that we write are still valid the entire time. Now, the kicker here is using this area. And this is a trapezoid. So when we do the area, right, here's the left-hand side of the trapezoid, which has a length of 5. Here's the right-hand side, which has a length described by this equation. And there's our time. So when we do this area calculation, we're going to get change in y equals 1/2 the left plus the right times the width, which is t. Now, this delta y is equal to y final minus y initial. Now, y initial is 0. So at t equals 0, the ball is at y equals 0. And we can clean this up as well. 5 plus 5 is 10. Divided by 2 is 5 times t. And then by time we multiply this and this, we get minus 4.9 t squared. So the math part of this is basically done. We have our equations now for velocity against time, position against time. I'm going to start answering these questions. Let's see, how long does it take before it hits the ground? So when that ball gets here, it is 10 meters below where it started. So its final y coordinate is -10. What I'm going to do is put that into this position function. I'm going to do the work over here. -10 equals 5t minus 4.9 t squared. And now it's just a matter of solving this for t. It's quadratic. So let's do this. Let's add, then subtract. Leave that one. And because it's quadratic, let's see, t is going to be the opposite of b, plus or minus the square root of. Now for b squared, I'm going to just save myself some writing, but 25 minus 4 times a times c. Now c is -10. I'm going to put the 10 here and just move the minus sign and put it right there, make that plus. Over twice 8, if you don't mind, twice 4.9 is 9.8. Now, I'm going to leave this as an exercise to the reader here, but if you do 5 minus this, you are going to get a negative number. Our functions start at t equals 0. The positive root should work out to be 2.02 seconds. 2 would be perfectly acceptable if this were my class in a quiz or a test. Some of these numbers were given like that's a one significant figure value anyway, but I'll just leave it at 2.02 and move on. All right, so there's the time when the ball hits the ground. Okay, the how high does it go? Let's chat about that. So the how high is referring to when the ball is here at the top of the curve. Now we can't really use this function because we don't know a y or a t. So let's take a look at this other one, our velocity function here. And what you have to realize is, right, the velocity was positive, and then 0, and then negative, right? So at the highest point right there, the velocity is 0. So we're going to take this function and write it 0 equals 5 minus 9.8 t. If we solve this for t, let's see, I get 5 over 9.8. Works out to seconds. I will save the working out of the units for another example. I get 0.51 out of this. seconds. And then we can run that 0.51 now through our position function. So the y coordinate is going to be 5 times 0.51 minus 4.9 times 0.51 squared. And it will work out to meters. I realize that some of you, particularly if you teach physics, are sticklers about units, and I am too for a lot of the time. But sometimes I find that people can get kind of hung up on the units too, and sometimes it can be, I think, detrimental for understanding what's going on as well. So I do kind of a mix of examples. You know, this 5 has units of meter per second. If I put these back in times seconds, this works out to meters. This number has units of meter over seconds squared, and this is times seconds squared as well. So it does work out to meters both times. Anyway, numerically, if you run this through, I get 1.27 meters. Now, for our maximum point, that is the height above here. This was not really clear. How high does it get? If this were a quiz question and I gave it to somebody, I'd be accepting that answer. If somebody gave me the distance from the ground and said 11.27 meters, I'd take that as well, because now you're just talking semantics. So again, just wanted to give an example of how to use this graphical kind of technique to analyze the motion of an object moving under the acceleration of gravity. I hope that this has helped. Have a great day.